Hello everybody, these are the video notes for 1.3, and these are going to be about geometric sequences. Let's start with an example sequence, and in this sequence it's going to be 4, then 8, then 16, then 32, etc. Okay. So now let's take a look at our numbers and first try to think about, okay, what is the pattern here? Usually the first thing that I try to do is figure out, are we adding by the same amount each time? Well, to get from 4 to 8, we're adding 4. So if I continue that pattern, 8 plus 4 would be 12, not 16, so that doesn't work. So we're not adding by the same number every time. There is no common difference. So let's try a different operation. Okay, well, it's getting bigger, so maybe it's multiplying. Let's try multiplication. 4 times what equals 8? Well, if I go backwards, 8 divided by 4, that would be 2. So that means 4 times 2 is equal to 8. Let's see if the pattern continues. 8 times 2 is equal to 16. That checks out. One more time. 16 times 2 is equal to 32. Great, we know the pattern. And this is how we know that it is a geometric sequence. I'm going to put a big multiplication sign at the top here to remind myself that the difference between arithmetic and a geometric sequence is an arithmetic sequence, you are adding by the same amount between each of the numbers. In a geometric sequence, you are multiplying by the same amount each time. In an arithmetic sequence, you have a common difference. And in a geometric sequence, this 2 that we're multiplying by each time, we call that the constant ratio. So this sequence has a constant ratio of 2. Now let's make a table. And let's put term number on the left. Call that n. And then we'll have the number value here. We'll call that f of n. Start with 0, 1, 2, 3, and 4, like that. Okay, so let's skip 0 for now. The first term of the sequence. Well, the first term of the sequence, that's going to be this 4 that I'm going over in purple. Okay, the first term is 4. Second term, 8. Third term, 16. Fourth term, 32. Now go ahead and draw a line here, because now we're going to write out how we got to each of these numbers in expanded form. So to get to the 4, we just started with the first term. We had 4. To get to the 8, we started with the 4 there, but we multiplied by the constant ratio of 2 once to get to 8. So I'm going to say we started with 4, and then we multiplied by 2 once. To get to the third term, we started with 4. Then we multiplied by 2 once, and then multiplied by 2 twice. So we have 4 times 2 times 2 twice. To get to 32, we started with 4 at the very beginning, and then multiplied by 2 once, twice, 3 times to get to 32. So we have 4 times 2 times 2 times 2. Notice that each of these numbers started with the same number, 4, and then multiply by the constant ratio a certain number of times. And any time that we have repeated multiplication, we can use exponents. 4, that's just the same thing as 4. 4 times 2, we can think of this as 4 times 2 to the first power. 2 to the first power is just 2. 4 times 2 times 2, we can think this as 4 times 2 to the second power, because we're multiplying by 2 times. This we can think of as 4 times 2 to the third power, because we multiply by 2 3 times. So then, if we wanted to go all the way out to the 50th term in the sequence, well, we know it would be 4 times 2 a whole bunch of times. How many times? Well, let's see the pattern that we can pick up here. To get to the second term, we multiplied by 2 once to the first power. To get to the third term, we multiplied by 2 twice to the second power. To the fourth term, we did 2 to the third power. So we're taking the constant ratio and raising it to a power 1 less than whatever the term number is. 1 less than whatever the term number is. Which means if it's the 50th term, we would multiply by the constant ratio 1 less than whatever the term number is. If the term number is 50, 1 less than 50 to the 49th power. That's how we would figure out the value of the 50th term. Okay, keep that in mind because that's going to help us out for the explicit function. Let's look at what the recursive function for this would look like. Well, same pattern as with an arithmetic sequence. We have to say where it starts. F of 1 is equal to, what's the first term? Well, it's 4. So we're starting at 4. And then we have to say what the pattern is. F of n is equal to f of n minus 1 times 2. Okay, let's annotate so you can get a sense of what all these numbers mean. This is saying the first term. That's where it starts. F of n, this is saying the current value of whatever term we're trying to find. F of n minus 1, that would be the previous term, the value of the previous term. And 2, that's the constant ratio. Right? In words, what this recursive function is saying is the first term is 4, and then each term value is equal to whatever the value of the previous term was, but times 2. That's how we get to the next term. Now let's talk about the explicit function. F of n, the term value is equal to. Now here's where we're going to use this kind of structure that we have in our table for the right here. We know that we started with 4, and then we multiplied it by our constant ratio of 2. And the number of times that we're multiplying by 2 is equal to 1 less than whatever the term number is. So if I'm trying to go all the way up to the nth term, then I have to multiply by 2, 1 less than whatever n is. So that's why I'm going to say to the n minus 1 power. Let's annotate. 4, that's the first term. and 2, that's the constant ratio. Okay. Last thing that I want to show you is another way that you can write the explicit function. We have the first term of 4, right? Now, what if we used the 0 term instead? Let's go back here. 4 is the first term. Now, what if we wanted to go backwards and figure out if there was a 0 term? What would it be? Well, based on the pattern, we know that's multiplying by 2 every time. So I can think to myself, what number times 2 is equal to 4? Well, I can also work backwards. 4 divided by 2 is equal to 2. So if we go to the 0 term, we know that that's 2. I'm going to fill that in here. And we can use that information. We can say f of n is equal to the 0 term of 2 times the constant ratio of 2 to the nth power, not n minus 1. Oops, sorry, you can't see that. Now you can. That's the 0 term. That's the constant ratio. I'm just going to put CR for constant ratio. So why is it to the nth power instead of n minus 1? Because if you start with the 0 term, the number of times that you have to multiply by the constant ratio is, you have to multiply the constant ratio one more time than if you started with the first term. So that's why it's to the nth power. Or another way of thinking about that is if you start with the first term, the number of times that you have to multiply by the constant ratio is 1 less than starting with 0 because you're already starting with the first term.